We can then move on to model interpretation. So now that we have built our model, we could try to see which features contributed the most or the least to predicting LDL cholesterol levels. As mentioned earlier, for this section, we use SHAP, which stands for Shapley Additive Explanations. Sadly, won't go into detail for this episode, but as a very brief, high-level explanation, essentially it judges a feature's contribution to a prediction based on the model's performance with that feature versus without that feature. So if the model performs much better with that feature versus being trained without that feature, then we can say that it's quite an important feature. And the bigger that gap, the more important the feature. To apply this model, we need to take a sample of our train and our test data. Ideally, we want to use all of this, but that can be very time consuming and you need quite a powerful computer. Alternatively, you could also use the cloud to run this. So here we take a sample of our pre-processed train data and pre-processed test data. So just focusing on the input features here. We then identify our class names. And for this, we use the deep explainer from SHAP. And for this section, we produce a B-swarm plot for each of our classes of low, okay, or high levels of LDL cholesterol. So what is a B-swarm plot? Some of you may be asking. Essentially, it ranks all of our features from the most important to the least important based on the method used in SHAP. And for each sample, it produces what's called the SHAP value, which essentially gives an impact on the model output. So a high SHAP value means that the feature is increasing the prediction. So for example, here with the low class, we can see that for humidity, there are some samples where a high value of humidity, so the feature value here is shown between red and blue. So high values of humidity are pushing up the prediction of low LDL cholesterol. So from this graph here, we can see that humidity is the most important feature for predicting LDL cholesterol according to SHAP, followed by temperature and followed by a few absorbance numbers. For the second class of OK LDL cholesterol, we can see again humidity and temperature, and a few of the same absorbance numbers are ranked quite highly, so absorbance 112, 117. And lastly, for high LDL cholesterol, again, humidity and temperature ranking first and second, followed by similar absorbance values being the most important in predicting this class. There are a few conclusions that we can make from these graphs. So first, according to SHAP, both humidity and temperature at the time of the blood spectroscopy readings are the two most important features in predicting LDL cholesterol levels. The absorbance values at 112, 117, 125, 3, and 98, and 6, which each correspond to different wavelengths of light, have strong predictive power of each level of LDL cholesterol. So these absorbance numbers appeared as the top 10 features for predicting each of our classes. We can also see, looking back at these graphs, that both red and blue values tend to appear on both sides of this x equals 0 line. Just to reiterate, so a higher SHAP value means that it's pushing the prediction up. So if it's positive, it's pushing the prediction up for that class, and if it's negative, it's pushing it down. So for example, if we look at our OK LDL cholesterol class, we can see that for one of the samples, a high value of humidity actually reduced the predicted probability for that class. But in general, we have both red values and blue values on either side, so you can't say for definite that a higher value of a certain feature increases the prediction or a lower value decreases the prediction. This happens when features interact with each other, so it's not the feature itself that increases or decreases prediction, but it's the feature in combination with something else. Another reason is that there isn't a linear relationship between our features and our target variable. So it might not be as the absorbance value increases at a certain wavelength, then the predicted probability goes up. It may be that at a certain range of absorbance values, it may increase the prediction. Then at another range that's slightly higher, it may decrease the prediction. And then at another range that's slightly higher, it may increase the prediction. So it's not necessarily linear. It could be quadratic.